Question number 16 is, consider real valued function f satisfying fx plus 1 equals fx for all x belongs to R. That means this function is periodic with period 1. We are given that gt is this integral from 0 to t fx dx, and we have defined this function ht as this limit n tends to infinite g t plus n upon n. Now if we look at gt plus n will be nothing but 0 to t plus n fx dx. Now we can write this as this integral from 0 to n fx dx plus n to n plus t fx dx. Now this function is periodic with period 1. So we can write this as n into this integral from 0 to 1 fx dx and then plus. Now this is from nt to nt plus a, and it will be from 0 to t fx dx. So we can write this function h as this limit n tends to infinite n, this integral from 0 to 1 fx dx plus this integral from 0 to t fx dx upon n. Now we split it in two parts. This n and n will cancel, and 1 upon infinite will be 0. So this ht will be nothing but will be this value from 0 to 1 fx dx, which is a constant function. So this ht, it is defined for all t belongs to R, and it is independent of t, and that's here option C. Now question number 8 is, let f be a real value differentiable function on the real line such that limit x tends to 0, fx upon x square exists and is finite. Prove that f dash 0 is 0. Now it is given that f is a differentiable function, so that means it is continuous also. Now if the function is continuous, we can write f0 as limit x tends to 0 fx. Now we can write this limit as limit x tends to 0 x square into fx by x square. So it will be limit x tends to 0 x square into limit x tends to 0 fx by x square. Now this is finite and it is 0. 0 into finite is 0. So value of f0 is 0. Now if f0 is 0, we can find f dash 0 as this limit h tends to 0 fh minus f0 upon h. Now f0 is 0, so we can write this as limit h tends to 0 h into fh upon h square. Now fh upon h square is finite and h is 0, so from here we can say f dash 0, it must be 0. Question number 7 is, by the binomial theorem, we can write root 2 plus 1 to the power 10. It is this summation I varies from 0 to 10 ci into root 2 to the power I. And if we have to get it in this form, we have to write this as 1 plus root 2 to the power 10, and it will be equal to this summation I varies from 0 to 10 ci into root 2 to the power I. Now it says we have to find the value of I for which this term is the largest term among all the 11 terms. So basically we have to find numerically greatest term. Now we have discussed this in one of the previous videos. If we have to find numerically greatest term for x plus a to the power n, we will find some alpha which is n plus 1 upon 1 plus mod x by a. So in this case, if we find this alpha, it will be 10 plus 1 upon 1 plus, now x is 1 and a is root 2. So it will be 11 root 2 upon root 2 plus 1, or we can write this as 11 root 2 into root 2 minus 1, which is nearly 6.44. And we know that if alpha is not an integer, then its numerically greatest term is given by t greatest near function of alpha plus 1, which is 7th term. And if the term is 7th one, if we write the expansion, it will be 10c6 into root 2 to the power 6. So in this case, value of I is going to be 6. Now we come to its second part. It says, for every natural number n, let root 2 plus 1 to the power n be pn plus root 2 qn, where pn and qn are integers. Then we need to find this limit n tends to infinite pn upon qn to the power 10. Now if we take this limit here, it will be infinite. So we won't get any result from this. What we'll do is, we know that if we take the expansion of root 2 plus 1 to the power n, it will be c0 root 2 to the power n plus c1 root 2 to the power n minus 1. And if we consider root 2 minus 1 to the power n, it will be c0 root 2 to the power n minus 1 to the power 0 minus c1 root 2 to the power of n minus 1. So the expansion of root 2 minus 1 to the power n will be nothing but pn minus root 2 qn. Now we take limits both sides. Now root 2 minus 1, it lies between 0 and 1. So a to the power n in that case, it will be simply 0. And here it will be limit n tends to infinite pn minus root 2 qn. We can also write this as limit n tends to infinite pn upon qn. It will be simply root 2, and then limit n tends to infinite pn upon qn to the power 10 will be root 2 to the power 10, which is simply 32. Now here we need to find the value of this limit, which is limit n tends to infinite n plus 1, this integral from 0 to 1 x to the power n log 1 plus x into dx. Now we'll take this log as first function and this x to the power n as second function. We can write this limit as limit n tends to infinite. Now it will be n plus 1, and here we'll use by parts. So first function as it is, and then it will be x to the power n plus 1 upon n plus 1 minus, now derivative first, so it is 1 upon 1 plus x, and then it will be x to the power n plus 1 upon n plus 1 into dx. Now we'll put the limits. Limits are from 0 to 1. Now here n plus 1 will cancel. So we can write this as limit n tends to infinite. Now we'll put x as 1, it will be log 2 minus 0, and then minus this integral from 0 to 1 x to the power n plus 1 upon x plus 1 into dx. So it will be log 2 minus this limit n tends to infinite from 0 to 1 x to the power n plus 1 upon x plus 1 into dx. Now when n tends to infinite, this x, it lies between 0 and 1. So this value will be nearly 0. So value of this integral is nothing but 0. So answer to this limit will be log 2, and that's your option number B. Here the question is fx is e to the power minus mod x, and we are given this g theta, which is integral from minus 1 to 1 f x upon theta, which is e to the power minus mod of x upon theta dx. Now this function, it is an even function, so we can write g theta as 2 times, and this integral from 0 to 1 e to the power minus mod x upon mod theta dx. Now when x is greater than 0, mod x is simply x. So it will be 2 times this integral from 0 to 1 e to the power minus x upon mod theta dx. Now if we integrate this function, we can write this as e to the power minus x upon mod theta upon minus 1 upon mod theta, this integral from 0 to 1. So we can write g theta as 2 times mod of theta and then 1 minus e to the power minus x upon mod theta. Now we need to find this limit, which is limit theta tends to 0 g theta upon theta, and there will be this limit theta tends to 0 2 times mod of theta upon theta, and here this value it should be 1 minus e to the power minus 1 upon mod theta. Now whether we take this as theta positive or theta negative, it will be e to the power minus infinite, and this will always be 0 for both left hand limit and right hand limit. Whereas this expression, it will be minus 2 in the case of left hand limit, and it will be plus 2 in the case of right hand limit. That means this limit does not exist, and that's your option D. Now question number 19 is, we need to find this limit n tends to infinite 1 plus 1 upon n square plus n to the power n square plus root n. Now this is 1 to the power infinite form, and if it is 1 to the power infinite form, we'll directly use shortcut, which is e to the power limit n tends to infinite gx, which is n square plus root n into fx minus 1, which is 1 upon n square plus n. So it will be e to the power this limit n tends to infinite n square plus under root n upon n square plus n. Now since it is an infinite limit, we look at highest power of n. Now coefficient of highest power of n in the numerator is 1 and the denominator is also 1. So it will be nothing but e to the power 1, that is e, and that's your option A. Now question number 24 is, let alpha greater than 0 and consider the sequence xn equals alpha plus 1 to the power n plus alpha minus 1 to the power n upon 2 alpha to the power n. Then limit n tends to infinite xn is. So we have to find this limit n tends to infinite, and xn is alpha plus 1 to the power n plus alpha minus 1 to the power n upon 2 alpha to the power n. Now what we'll do is, we'll consider this limit in 2 parts. We'll write limit, and if we take this first part, it will be 1 by 2 plus 1 by 2 alpha to the power n plus limit n tends to infinite 1 by 2 minus 1 by 2 alpha to the power n. Now we consider this first limit, which is limit n tends to infinite 1 by 2 plus 1 by 2 alpha to the power n. Now if we take alpha as 1, this value will be simply 1. If we take alpha greater than 1, in that case, this expression will be less than 1. Now a to the power infinite when a is less than 1 is nothing but 0. And if alpha is less than 1, in that case, this value will be greater than 1. Then a to the power infinite will be simply infinite. So this first limit will take the values 1, 0 and infinite depending on the value of alpha. Now for the second limit, which is limit n tends to infinite 1 by 2 minus 1 by 2 alpha to the power n. Now if we take this first case, when 1 by 2 minus 1 by 2 alpha, it lies between minus 1 and 0. Now this value will be minus 3 by 2. It will be less than minus 1 upon 2 alpha, and it will be less than minus 1 by 2. 3, it will be greater than 1 by alpha, and it will be greater than 1. And if we take reciprocal, we'll get alpha is greater than 1 by 3 but less than 1. In that case, this value, it will lie between minus 1 and 0. Then in that case, e to the power infinite will be simply 0. So for this case, value of this limit is simply 0. Now if we take alpha as 1 by 3, we'll get this value as minus 1. So it will be minus 1 to the power n. Then this limit, it will oscillate between minus 1 and plus 1. And if alpha is less than 1 by 3, then this expression, it will be less than minus 1. And if it's less than minus 1, then this limit, it will oscillate between minus infinite and plus infinite. Now, if we add these two limits, then this limit n tends to infinite xn, it will take this value 0 when alpha is greater than 1, it will be 1 when alpha equals 1, and it will be infinite when alpha is less than 1. So this limit xn will take the value 0, 1 or infinite depending on the values of alpha, and which is your option D. And question number 11, we are given the sequence which is fnx equals x to the power n cos 2 pi nx when x belongs to minus 1 and plus 1. And we need to find this limit n tends to infinite fnx. Now if we consider this first case, when the value of x is 1, we can write fn1 as 1 into cos 2n pi, and cos 2n pi is 1. So in this case, limit n tends to infinite fnx will be simply 1. So for x equal to 1, this limit exists. Now we'll consider the second case when the value of x is minus 1. Now we'll have fn minus 1, and it will be minus 1 to the power n cos 2n pi into minus 1, which is minus 1 to the power n. Now we take this limit n tends to infinite fnx, then in that case this value, it can be either minus 1 or plus 1. That is, we'll get an oscillating value. So in this case, this limit, it does not exist. And finally, when x lies between minus 1 and plus 1, in that case, this mod xn cos 2n pi x will be mod of x to the power n into mod of cos 2n pi x. And if we take this limit n tends to infinite, now this is oscillating value from 0 to 1, and since mod x, it lies between 0 and 1, this is 0. Now 0 into anything finite is simply 0. In this case also, this limit exists. So this limit will exist if and only if x belongs to the interval where minus 1 is not included and 1 is included, and that's your option D. Now question number 20 is, this function from R to R be a non-zero function such that this limit x tends to infinite fxy upon x cube exists for all y greater than 0. Let gy equals this limit x tends to infinite fxy upon x cube. Now it is given that g1 is 1. So we'll put y as 1. We can write limit x tends to infinite fx upon x cube, it is equal to 1. Now we'll need to find gy. Now what we'll do is, we'll write this gy as this limit x tends to infinite fxy, and here we'll write this as xy cube into y cube. Now we can write this gy as y cube into limit x tends to infinite fxy upon xy cube. Now when x tends to infinite, xy also tends to infinite, so this limit, its value is 1. So we can write this function gy, it must be this function y cube, and that's your option D. Now question number 5 is, let a1 be greater than a2 be greater than ar, then we need to find this limit, which is limit n tends to infinite a1 to the power n plus a2 to the power n plus ar to the power n to the power 1 by n. Now we know that we can write this a1 as a1 to the power n to the power 1 by n, and it will be less than a1 to the power n plus a2 to the power n plus ar to the power n whole to the power 1 by n. Now each of ai, it is always less than a1, so it will be less than r into a1 to the power n to the power 1 by n. So from here we can write a1 is less than a1 to the power n plus a2 to the power n plus ar to the power n to the power 1 by n will be less than r to the power 1 by n into a1. Now we'll take this limit n tends to infinite. Now this limit is a1, this limit is also a1. So from sandwich theorem we can say that the value of this limit will be simply a1. Now question number 21 is, suppose phi is the solution of this differential equation such that phi 0 is 1 and phi dash 0 is 5, then which of the following option is correct? Now we are given a second order differential equation. We can write this as m square minus m minus 2 equals 0. So it will be m minus 2, m plus 1 equals 0. So value of m is 2 or value of m is minus 1. So we can write this phi x as a into e to the power 2x plus b into e to the power minus x. Now we're given that phi 0 is 1. So phi 0 is a plus b, and it is equal to 1, and phi dash 0 will be 2a minus b, and it is 5. Now if we'll add them, we'll get a as 2, and if the value of a is 2, value of b is minus 1. So we can write this phi x as 2 into e to the power 2x minus e to the power minus x. Now if x tends to infinite, then in that case this expression will be plus infinite and this expression here will be 0. So if x tends to plus infinite, then phi also tends to plus infinite. Now as x tends to minus infinite, in that case here it will be 0 and minus, and L tend to infinity. So if x tends to infinite, then phi also tends to infinite. So the correct option is, as x tends to minus infinite, phi also tends to minus infinite, and that's your option C. Now question number 22 is, we need to find this limit t tends to 0 f u plus tv minus f u upon t. Now u is 1 by 2 comma 1 by 2 and v is 3 comma 4. Now u plus tv, it will be 1 by 2 plus 3t comma 1 by 2 plus 4t. So we have to find this limit, which is limit t tends to 0 f 1 by 2 plus 3t comma 1 by 2 plus 4t and minus f 1 by 2 comma 1 by 2 by t. Now fxy is x square into y minus 1. So we can write this as limit t tends to 0, 1 by 2 plus 3t whole square into 1 by 2 plus 4t minus 1, and then minus will be 1 by 4 into minus 1 by 2 upon t, which is 0 upon 0 form. Now before taking L'Hopital's rule, we'll write this as 4t minus 1 by 2. Now we'll differentiate the numerator and denominator separately. We can write this as limit t tends to 0, and this is 2 into 1 by 2 plus 3t into 3, and then 4t minus half, and then plus 1 by 2 plus 3t square into 4 minus 0 upon 1. Now if we put t as 0, we'll get this as minus 3 by 2 and then plus 1, which is minus 1 by 2. So answer to this limit will be minus 1 by 2, and that's your option C. Now 23 years, we are given a real number alpha which lies between 0 and 1, and we have defined a sequence such that xn plus 1 equals alpha xn plus 1 minus alpha xn minus 1. Now what we'll do is we'll subtract xn. We can write xn plus 1 minus xn will be alpha minus 1 and then xn minus xn minus 1. Now in the same way we can write this as alpha minus 1 square into xn minus 1 minus xn minus 2, and if we continue this iteration we can write this as alpha minus 1 to the power n x1 minus x0. So we can write xn plus 1 minus x0 will be alpha minus 1 to the power n x1 minus x0. Now in the same way we can write xn minus xn minus 1 will be alpha minus 1 to the power n minus 1 x1 minus x0, and finally we'll get x1 minus x0 as alpha minus 1 to the power 0 x1 minus x0. Now if we add them all up, on the left hand side we can write xn plus 1 minus x0, it will be x1 minus x0 into 1 plus alpha minus 1 plus alpha minus 1 square up to alpha minus 1 to the power n. Now what we'll do is we'll take this limit n tends to infinite. So it will be this limit n tends to infinite xn plus 1 minus x0, and here will be x1 minus x0, and then this series which is nothing but an infinite GP whose sum is a upon 1 minus r, which is 1 minus alpha minus 1. So it will be x1 minus x0 upon 2 minus alpha. We can write this limit n tends to infinite xn plus 1 as x1 minus x0 upon 2 minus alpha and then plus x0. So it will be x1 plus 1 minus alpha x0 upon 2 minus alpha. x1 plus 1 minus alpha x0 upon 2 minus alpha, and that's your option B. Now question number 9 is we need to find these limits. Now for this function fx, if we take this limit x tends to 0, x upon x plus sin x, now we can write this as 1 upon 1 plus sin x upon x. Now sin x upon x is 1, so this value is 1 by 2, so this option A is correct. Now if we take this limit x tends to infinite, in that case we can write this as limit x tends to infinite. This is 1 upon 1 plus sin x upon x. Now this is oscillating value minus 1 to 1 upon infinite, so it will be 0. So in this case value of this limit is 1. So this limit, it exists. So this option B is incorrect. If we take this limit extends to infinite, we can write limit extends to infinite x to the power 4 plus x to the power 6 upon e to the power x minus 1 minus x square infinity upon infinity form. Now if we keep using L'Hopital's rule, then we can write this as limit x tends to infinite. It will be factorial 6 upon e to the power x. Now e to the power infinite is infinite. So anything finite upon finite will be 0. So this limit x tends to infinite, gx is finite. So this option C is also correct. Now we look at this option D, limit x tends to 0, gx. Now we use L'Hopital's rule in this. We can write limit x tends to 0. Now this is 4x cube plus 6x to the power 5. Now this is e to the power x minus 2x. Now this limit, it is 0. So this option D, it is incorrect. So the correct options are A and C. Now question number 19 is, we'll need to find this limit, which is limit n tends to infinite, then summation k varies from 1 to n, and this is e to the power 2 pi by n into iota k minus e to the power 2 pi iota k minus 1 upon n. Now for the sake of brevity, we'll write 2 pi by n as some theta. So we can write this as summation e to the power iota k theta minus e to the power iota k minus 1 theta. And this summation, it varies from 1 to n, where limit n tends to infinite. Now here we'll take e to the power iota k minus 1 theta common. So we'll take it common. We can write limit n tends to infinite, summation k varies from 1 to n, and then mod of e to the power iota k minus 1 theta, and then e to the power iota theta minus 1. Now modulus of e to the power iota theta is simply 1. So this value will be 1. So we can write this as limit n tends to infinite, and then summation k varies from 1 to n mod of e to the power iota theta minus 1. Now this expression, it is independent of k. So it will actually be limit n tends to infinite n into mod of e to the power iota theta minus 1. Now we'll put the value of theta. Theta is 2 pi by n. So we can write this limit as limit n tends to infinite e to the power 2 pi by n iota minus 1, and this mod upon 1 by n. Now we'll multiply and divide it with mod of 2 pi iota. So this limit, it is standard limit e to the power x minus 1 upon x, which is 1, and then mod of 2 pi iota is simply 2 pi. So answer to this limit is simply 2 pi, and that's your option number C. Now question number 20 is, we need to find this limit, which is limit n tends to infinite 1 minus 1 upon n square to the power n. Now form of this limit is 1 to the power infinite, and if the limit is of the form 1 to the power infinite, we can use the direct shortcut, and which is limit x tends to a fx to the power gx. If it is of the form 1 to the power infinite, we can write this as e to the power limit x tends to a gx into fx minus 1. So we'll use the same shortcut here. So it'll be limit n tends to infinite e to the power, now gx is n, and then fx minus 1. So 1 minus 1 upon n square minus 1 will be simply 1 minus n square. So here n and n will cancel. So we'll get limit n tends to infinite e to the power minus 1 by n. Now this is e to the power 0, and e to the power 0 is 1, and that's your option number D. Now question number 5 is, we are given this limit n tends to infinite 1 plus a by n plus b by n square to the power 2n, and it is equal to e square. We need to find the value of a and b. Now this is 1 to the power infinite form. We'll directly use shortcut, which is e to the power limit n tends to infinite, gx, which is 2n, into fx minus 1, which is a upon n plus b upon n square, and it'll be equal to e square. And we'll multiply n and n, will cancel. So this limit will be simply e to the power 2a, which is equal to e square. That means value of a is 1, and this limit, it doesn't depend on b. So b can be any real number. So answer to this limit will be a equals 1 and b is any real number, and that's your option C. Now question number 7 is, let x naught greater than 0 and xn be defined recursively by xn equals under root of 6 plus xn minus 1, where n is greater than or equal to 1, then this limit n tends to infinite xn is. Now we can write this xn as under root of 6 plus xn minus 1. We can write this as xn square, it will be 6 plus xn minus 1. Now what we'll do is we'll subtract xn minus 1 square from it. So it will be xn square minus xn minus 1 whole square, and if we take minus common here, we'll get xn minus 1 square minus xn minus 1 minus 6, and if we factorize it, we can write this as xn minus 1 minus 3 and xn minus 1 plus 2. Now here critical points are 3n minus 2, and since x naught is greater than 0, we'll take two cases. Case 1, if x naught is less than 3, and case 2, if x naught is greater than 3. Now if x naught is less than 3, then if we add 6, we'll write 6 plus x naught will be less than 9, that is under root of 6 plus x naught will be less than 3. We can write x1 will be less than 3, and using same iteration we can write xn will be less than 3. Then in that case this function will be bounded above. Now if xn is less than 3, then this value will be negative, this value will be positive, and then we have this minus sign here, so it will be minus and minus plus. So we can write xn square minus xn minus 1 square, and it will be greater than 0, that is xn is greater than xn minus 1, that is the sequence is monotonic increasing. So if the sequence is bounded above and increasing, that means this sequence, it is going to converge. Now what about the second case? And the second case, when x naught is greater than 3, if we add 6, we'll get 6 plus x naught will be greater than 9 under root of 6 plus x naught will be greater than 3, that is x1 is greater than 3. If we add 6, again if we take square root, we'll get x2 greater than 3. So from here we'll get this xn, it should be greater than 3. So in this case it is bounded below. Now if xn is greater than 3, then this expression will be positive, this is also positive, and here we have this minus sign. So we'll get xn square minus xn minus 1 square, it should be less than 0, that is xn, it should be less than xn minus 1. That means this sequence is now a decreasing sequence. So if the sequence is bounded below and monotonic decreasing, that means this sequence, it will converge. Now what about if x naught is 3? If x naught is 3, then this sequence will be a constant sequence, and we know that a constant sequence is a convergent sequence. So this sequence will be convergent for all the possible values of x naught. Now we'll need to find this limit n tends to infinite xn. For that, what we'll do is we'll take this limit n tends to infinite both sides. Now suppose this limit is L. So we can write L equals under root of 6 plus L, that is L square minus L minus 6 equals 0. That is the value of L is either 3 or The value of L is minus 2. Now since this sequence, it contains positive terms, its limit point cannot be negative. So for this sequence, the value of this limit is simply 3. So this limit n tends to infinite xn will be 3, and which is none of the above, option D. Now question number 12 is, let alpha and beta be distinct roots of this equation. Now we can write this equation as a into x minus alpha into x minus beta equals 0. We are given this limit x tends to alpha 1 minus cos ax square plus bx plus c upon x minus alpha whole square. Now this is 0 upon 0 form. Now we'll use standard limit. So we can write limit x tends to alpha, and this is 1 minus cos ax square plus bx plus c upon ax square plus bx plus c whole square into ax square plus bx plus c whole square upon x minus alpha square. Now this is standard limit, which is 1 by 2, and we can write this as limit x tends to alpha. Now we'll write this equation as ax minus alpha into x minus beta. So it will be a square x minus alpha square into x minus beta square upon x minus alpha square. Now this alpha will cancel. So we'll get this limit as 1 by 2 a square into alpha minus beta whole square, and that's your option C. 55 is, let a n be a sequence of real numbers, then limit n tends to infinite a n exists if and only if. Now which of the following option is correct? Now what we'll do is, we'll say, suppose this limit n tends to infinite a to n, it is say L1, limit n tends to infinite a 2n plus 1, it is suppose L2, and this limit n tends to infinite a 3n, and suppose this is L3. Now we consider this sequence, which is a 6n, then a 6n is a subsequence of a 2n because it is a multiple of 2n. So we know that any subsequence will converge to the same limit. So the subsequence, it will converge to L1. Now 6n is also a multiple of 3n. So that means the 6n is again a subsequence of a3n. So that means it will converge to L3. So from here we can say L1 must be equal to L3. Now let us consider another sequence, which is a 6n plus 3. Now a 6n plus 3, it is subsequence of a 3n. So that means it will converge to L3. And we can also write a 6n plus 3 as 2 into 3n plus 1, which is of the form 2n plus 1. So that means it is a subsequence of a 2n plus 1. It also converges to L2. So from here we can say L3 must be equal to L2. So L1 must be equal to L2 must be equal to L3. Now L1 is equal to L2. So that means from here we can say these both a2n and a2n plus 1, they converge to same limit. So that means this limit n tends to infinite, it also converges to the same limit. So answer to this question is option number C. Now question number 56 is, if a and b is sequence of non-negative real numbers such that the series n varies from 1 to infinite an is convergent, if p is a real number such that the series summation under root an upon n to the power p diverges, then which of the following is true? Now from Cauchy-Schwarz inequality we can say that this summation under root an upon n to the power p, it is less than or equal to summation an whole to the power 1 by 2 and this summation 1 upon n to the power 2p to the power 1 by 2. Now it is given that this series diverges and summation an, it is a convergent sequence. So that means this sequence, which is summation 1 upon n to the power 2b, it must be a divergent sequence. Now we know that this sequence diverges when the value of 2p is less than or equal to 1. That is, the value of p should be less than or equal to 1 by 2. And that's your option number B. Now question number 57 is, consider the sequence an and it is ea to the power 1 by n minus a to the power 1 by n upon 1 by n. Now we need to find this limit, which is limit n tends to infinite an. So we can write this as limit n tends to infinite and then ea to the power 1 upon n minus a to the power 1 upon n upon 1 by n. Now what we'll do is we'll let 1 upon n as t, then we can write this limit as limit t tends to 0 ea to the power t minus a to the power t upon t. Now this is 0 upon 0 form, so we can use L'Hopital's rule. So we can write limit t tends to 0 ea to the power t into log ea minus a to the power t into log a. Now we'll put t as 0, so we'll get this as log ea minus log a. So it'll be simply ln e, and ln e is nothing but 1. So answer to this limit is 1, which is none of the above, option number D. Now question number 58 is, let an be a sequence of real numbers satisfying mod an is less than or equal to 1 for all n. We define an as 1 by n a1 plus a2 plus an. Then for n greater than or equal to 1, we need to find this limit n tends to infinite under root n an plus 1 minus an. Now we look at this limit, we can write this as limit n tends to infinite. Now under root n, now what is an plus 1? It is nothing but it is 1 upon n plus 1 a1 plus a2 plus an plus an plus 1 minus 1 upon n a1 plus a2 plus an. Now we'll take LCM, we can write this as limit n tends to infinite under root n. Now LCM will be n plus 1 into n, and here will be n a1, n a2 and n an plus 1. So here we'll get n a n plus 1. Now n a1 minus n plus 1 a1. So it'll be minus a1 minus a2 and minus an. Now we know that for any an, its modulus is always less than or equal to 1. So we can say this limit is less than or equal to limit n tends to infinite under root n upon n plus 1 into n, and here we can write this as n mod an plus 1 plus mod a1 plus mod a2 plus mod an. Now maximum value of any an is 1, so we can write this is less than or equal to limit n tends to infinite, and this is under root n. Now this is n, and then maximum value for each is 1, so it will be 1 plus 1 plus 1 up to n upon n plus 1 into n. So we can write this as limit n tends to infinite under root n into 2n upon n plus 1 into n. This n will cancel. Now power in the numerator is less than power in the denominator, so that means this limit will be 0. So from here we can say that this limit, it must be equal to 0, and that's your option number A. Now question number 4 is, we need to find this limit un as n tends to infinite. Now this un is nothing but agp. So we can write this limit of un as n tends to infinite as some value, say s. Now s is equal to 1 upon 2 plus 2 upon 2 square 3 upon 2 cube, and this sequence will continue up to infinite. Now we'll again write the sequence by shifting one term, and we'll multiply it with 1 by 2. So here it will be 1 upon 2 square, here will be 2 upon 2 cube up to infinite. Now we subtract second sequence from first, we'll write s by 2, and it will be 1 by 2 plus 1 by 2 square plus 1 by 2 cube up to infinite. So it will be s by 2, and this is nothing but infinite GP, which is a upon 1 minus r, that is 1. So value of s is simply 2. So this limit n tends to infinite un, it is nothing but 2, and that's your option B. Now question number 73 is, if a function fx is a differentiable function such that limit x tends to infinite fx is 1 and limit x tends to infinite f dash x is alpha, we need to find the value of alpha. Now what we'll do is we can write f n plus 1 minus fn as f n plus 1 minus fn upon n plus 1 minus n. Now this is nothing, it is slope of this function at some point. This is equal to some f dash c where c belongs to n comma n plus 1 using Lagrange's mean value theorem. Now we'll take this limit n tends to infinite f n plus 1 minus fn. It will be this limit n tends to infinite f dash c. Now when n tends to infinite, this limit, it is equal to 1. So it is 1 minus 1, and then this limit, which is limit n tends to infinite f dash c. Now when n tends to infinite, this c also tends to infinite. So basically this n tends to infinite f dash c is nothing but alpha. So this is alpha. So from here we can say value of alpha, it must be 0, and that's your option number A. Now question number 6, it is a very simple L'Hopital's rule question. It says we need to solve this limit. Now we'll put x as a, it is GA FA minus FA GA upon A minus A. So it is 0 upon 0 form. So we'll use L'Hopital's rule. We can write limit x tends to A, and here it will be G dash x into FA minus F dash x into GA upon 1. Now we'll put the value of x. So it will be G dash A into FA minus F dash A into GA. Now what's G dash A? G dash A is 2. What's FA? FA is also 2 minus F dash A, it is 1, and GA is minus 1. So it will be 4 plus 1, and that will be 5, and that's your option number D. Now question number 22 is, we are given this an, which is 1 minus 1 upon root 2, 1 minus 1 upon root 3 up to 1 minus 1 upon root n plus 1. We need to find this limit n tends to infinite an. Now we know that one minus 1 upon root 2 is less than 1 upon 1 minus root 3 is less than 1 upon 1 minus root 4, and will be less than 1 upon 1 minus under root of n plus 1. Now we know that all the terms, they are greater than 1 minus 1 upon root 2. So if we'll replace all the terms in the product with 1 minus 1 upon root 2, we can say that an is always greater than 1 minus 1 upon root 2 to the power n. It will always be less than its maximum value. Maximum value is 1 minus 1 upon under root n plus 1, and then again n times. Now we'll take this limit, which is limit n tends to infinite. Now this expression, it is less than 1. Now when a is less than 1, then a to the power infinite is simply 0. Now what about this right hand limit? This right hand side limit, it is of the form 1 to the power infinite. So again we'll use shortcut. So it will be e to the power limit n tends to infinite, and then n and fx minus 1 will be under root of n plus 1. So this value, it will be e to the power minus infinite, which again is 0. So this limit on the left, it is 0, and this limit on the right is also 0. Then from sandwich theorem, we can say that this limit n tends to infinite an, it will be 0, and that's your option number D. Now question number 24 is, this series converges to which expression? So we know that this is telescopic summation. We can write this as k varies from 2 to infinite, and this is 1 upon k minus 1 minus 1 upon k. So it will be k minus 1. So we'll take k as 2, we'll get this as 1 minus 1 upon 2. If we'll take k as 3, we'll get 1 upon 2 minus 1 upon 3, and then 1 upon 3 minus 1 upon 4. It will continue up to infinite. All these successive terms, they'll cancel. So answer to this series will be 1. So this series converges to 1, and that's your option number B. Now question number 25. Again it is 1 to the power infinite form. So we'll use shortcut. So it will be e to the power, then limit x tends to infinite, and then gx, which is 4x, and fx minus 1. So it will be 3x minus 1 upon 3x plus 1 minus 1. So we'll get this as limit x tends to infinite, and here it will be minus 8x upon 3x plus 1. Now this is an infinite limit. Highest power is x. So this limit will be e to the power minus 8 by 3, and that's your option number C. Now question number 26, it is nothing but limit of sum. So we can write this as summation 1 by n, and then n upon n plus r, where r varies from 1 to n. So we can write this as summation r varies from 1 to n, 1 by n, and this is 1 upon 1 plus r by n. Now we'll replace this summation with integral sign. Now we'll replace r by n with x. So it'll be 1 upon 1 plus x, and 1 by n is nothing but dx. Now limits, when r is 1, it is 1 by n, which is 0, and then n upon n, it is 1. So it'll be simply log 1 plus x from 0 to 1, which is nothing but log 2. So the value of this limit is log 2, and that's your option number C. Now question number 23 is, we need to find this limit n tends to infinite fractional part of 3 plus 2 root 2 to the power n. Now what we'll do is, we'll say, suppose its integral part is r and fractional part is f, we can write this as 3 plus 2 root 2 to the power n. Now this is nc0, 3 to the power n, plus nc1, 3 to the power n minus 1, 2 root 2, and so on. And then we'll consider this f, which is 3 minus 2 root 2 to the power n. It lies between 0 and 1. This capital F, it lies between 0 and 1. And here also, any fractional part, it lies between 0 and 1. Now, if we add them, we can write r plus f will be 2 times 3 to the power n plus nc2, 3 to the power n minus 2 into 2 root 2 square. Now this right hand side, it is integer. This r, it is also an integer. That means this f plus f, it must also be an integer. Now if we add capital F plus small f, it lies between 0 and 2, and the only integral value possible in this case is 1. So we can write this small f as 1 minus capital F, or fractional part of 3 plus 2 root 2 to the power n will be 1 minus 3 minus 2 root 2 to the power n. Now we'll take this limit n tends to infinite. Limit n tends to infinite. And this is 1, and this value, it lies between 0 and 1. So a to the power infinite in this case will be simply 0. So answer to this limit is 1, and that's your option B. Now this third question is, we are given that fx plus 1 equals 1 by 2 fx. Now let an equals from 0 to n fx dx. We need to find this limit n tends to infinite an. Now in this equation, if we put x as x plus n minus 1, then we can write fx plus n as 1 by 2 f x plus n minus 1 will be equal to 1 upon 2 square f x plus n minus 2, and using iteration it will eventually come to 1 upon 2 to the power n into fx. Now we need to find this integral an, which is from 0 to n fx dx. Now we need to find this limit n tends to infinite an, which is this summation r varies from 0 to infinite integral from r to r plus 1 fx dx. Now what we'll do is, we'll replace x with t plus r, then we can write this as this summation r varies from 0 to infinite. Here will be from 0 to 1 ft plus r dt. Now using this relation we can write f t plus r as 1 upon 2 to the power r into ft. So it will be this summation r varies from 0 to infinite 1 upon 2 to the power r, then this integral from 0 to 1 ft dt. Now this is nothing but an infinite GP. Now sum of this GP will be a upon 1 minus r into this integral from 0 to 1. Now ft dt is same as fx dx. So we can write this as 2 times this integral from 0 to 1 fx dx, and that's your option D. Now question number 81 is, if f is continuous from 0 to 1, we need to find this limit. Now we see j by n, we know that j by n it corresponds to x and 1 by n it corresponds to tx. So we can change this limit into this integral, which is fx into dx. Now here x is j by n. Now we need to find limits of this function. When j is 0, clearly x is 0. So lower limit is 0. Now what about its upper limit? Its upper limit will be x equals greatest integral function of n by 2 upon n when this limit n tends to infinite. Now we know that greatest integral function of x is x minus fractional part of x. So it will be limit n tends to infinite n by 2 minus fractional part of n by 2 upon n. So it will be 1 by 2 minus this limit n tends to infinite fractional part of n by 2 upon n. Now fractional part, it always lies between 0 and 1. So anything finite upon infinite is 0. So the value of this limit is 0. So the upper limit of this function will be 1 by 2. So we can write this limit as this integral from 0 to 1 by 2 fx dx, and that's your option number D. Now question number 14 is, let Vn be a sequence defined by V1, which is 1, and then Vn plus 1 equals under root of Vn square plus 1 upon 5 to the power n. Then we need to find this limit n tends to infinite Vn. Now we can write Vn plus 1 square minus Vn square as 1 upon 5 to the power n. Now we'll put n as 1, we'll get V2 square minus V1 square, it is 1 by 5. If we'll put n as 2, we'll get V3 square minus V2 square, it'll be 1 upon 5 square, and then we can write Vn square minus Vn minus 1 square, it'll be 1 upon 5 to the power n minus 1. Now we'll add them. Now we'll add them, all these terms they'll cancel. From here we can write Vn square minus V1 square, and it will be 1 by 5 plus 1 upon 5 square plus 1 upon 5 to the power n minus 1. So we can write Vn square as, now V1 is 1, 1 plus 1 by 5, 1 by 5 square, 1 upon 5 to the power n minus 1. Now we need to find this limit, limit n tends to infinite Vn. So we'll find limit n tends to infinite Vn square. It is nothing but, it is this infinite GP. So we know that sum of infinite GP is a upon 1 minus r. So from here we can write Vn square limit n tends to infinite, it will be 1 upon 1 minus 1 by 5, which is 5 by 4. So this limit n tends to infinite Vn will be simply root 5 by 4, and that's your option number B. Now question number 27 is, for alpha belongs to 0 to 3 by 2, define xn as n plus 1 to the power alpha minus n to the power alpha. We need to find this limit n tends to infinite xn. Now if the value of alpha is 1, then clearly in that case xn will be n plus 1 minus n, which is 1, and if we'll take this limit n tends to infinite, simply it'll be 1. Now when alpha is not equal to 1, then in that case we can write this xn as n to the power alpha 1 plus 1 upon n to the power alpha minus 1. We can write this as 1 plus alpha upon n, alpha minus 1 upon factorial 2, 1 upon n square, and then minus 1. Now this 1 and 1 will cancel. So we can write this as limit n tends to infinite xn, and it will be limit n tends to infinite alpha into n to the power alpha minus 1 plus alpha minus 1 upon factorial 2 n to the power alpha minus 2. Now if alpha lies between 0 and 1, all these powers of n, they'll be simply 0. In that case, the value of this limit, it will be simply 0. But if alpha lies between 1 and 3 by 2, then this n, it will have a positive power, and when it'll have a positive power, then this xn will approach infinite. So answer to this limit will be 1, 0 or infinity depending on the value of alpha, and that's your option D. Now question number 16 is, we are given a sequence of real numbers xn such that subsequence x2n and x3n, they converge to limits k and l respectively, then which of the following option is true? So it is given that sequence of x2n, it converges to k, and sequence of x3n, it converges to l. Now we consider a sequence x6n. Now this 6n is actually a subsequence of 2n, and we know that any subsequence will converge to same limit. So x6n will also converge to k. Now 6n is also a multiple of 3n, so that means this x6n, it is also a subsequence of x3n, so its limit must also converge to l. So from here we can say that value of k must be equal to value of l. So k is equal to l. Now what about convergence of xn? Now if x2n and x3n, they converge, that doesn't mean xn will converge. So we can take this example. Say we are given the sequence xn, and xn is 1 when n is relatively prime 2, 6 and 0 otherwise. So if we write the sequence x2n, then it'll contain all these numbers 1, 1, 1, 1. So this sequence will converge to 1, and also x3n will converge to 1, but then xn, it does not converge. So answer to this question will be xn may not converge, but k is equal to l, and that's your option number C. Question number 5 is, now question number 5a is, we need to find this limit. So we'll take log both sides. We can write log a as this limit n tends to infinite. Now this power will come out, so it'll be 1 by n, and then log sine pi upon 2n into sine 2 pi upon 2n up to sine n pi upon 2n. Now we know that log m into n is log m plus log n. So we can write this as log a, and it will be equal to this limit n tends to infinite 1 by n, and we can write this as summation log sine pi r upon 2n, where the value of r varies from 1 to n. Now this is nothing but limit of sum. So we can write this as log a equals to limit n tends to infinite. Now we'll change this summation into this integral form. It will be log, now sine pi by 2 r upon n. We'll take r upon n as x, so it will be log sine pi upon 2x into dx. Now what are the limits? Lower limit is when the value of r is 1, so it will be 0, and upper limit is 1. So value of this limit will be this integral. So we can write log a as this integral from 0 to 1 log sine pi by 2x into dx. Now what we'll also do is we'll let pi by 2 into x as some t. So we can write log a. Now here will be log sine t, and then derivative of dx will be 2 upon pi dt. So it will be 2 upon pi dt, and this limit will change from 0 to pi by 2. So we can write log a equals 2 upon pi, this integral from 0 to pi by 2 log sine t dt. Now this is standard integral. We know that value of this integral is minus pi by 2 log 2. So here pi and pi will cancel, 2 and 2 will also cancel. So we can write log a equals minus log 2, that is the value of a is simply 1 by 2. So answer to this question is the value of this limit is simply 1 by. Now question number 6a is we are given this function fx, which is the summation n varies from 0 to infinite x to the power n factorial n to n minus 1 by 2. We need to find the value of this limit, which is limit x tends to 0 fx minus e to the power x upon 1 minus cos x. Now if we'll write the series, we can write the series of fx as when n is 0, this is x to the power 0, which is 1, factorial 0 is 1, and 2 to the power 0 is 1, so it will be 1 plus. Now we'll take n as 1, it will be x, and then here it will be 1, and then 2 to the power 0 is 1, so it will be x upon 1 plus, for n equals 2, it will be x square, and here it will be factorial 2 and 2 to the power 1, so it will be x square upon 4 plus, we'll use this big O notation, x cube. In the same way, we can write expansion of e to the power x, it will be 1 plus x square upon 2 plus ox cube, and for cos x, it will be 1 minus x square upon factorial 2 plus o x to the power 4. Now we'll find this limit. So this limit is limit x tends to 0. Now for fx, we'll write 1 plus x square by 4, and for e to the power x, it will be 1 plus x square by 2, and then ox cube, and here 1 minus cos x will be 1 minus x square upon 2 plus o x4. Now here 1 plus x will cancel, and in the denominator 1 and 1 will cancel. We'll write limit x tends to 0. Now this is x to the power 4. Now this is x square upon 4 minus x square upon 2, so it will be minus x square upon 4 plus other higher powers of x, and here it will be x square upon 2 and other higher powers of x. Now this is limit x tends to 0. So lowest power in the numerator is same as lowest power in the denominator. So answer to this limit will be simply minus 1 by 4 upon 1 by 2, which is minus 1 by 2. So value of this limit is minus 1 by 2. Now question number 30 is we are given this function from 0 to 1 to minus 1 to 1, and it will be a non-zero function such that f2x is equal to 3fx when x lies between 0 and 1 by 2. We'll need to find this limit x tends to 0 positive fx. Now what we'll do is we can write this fx as 1 by 3 f2x. Now we can write f2x as 1 upon 3 square into f 2 square x, and if we continue the iteration, we can write this as 1 upon 3 to the power n f 2 to the power of n into x. Now we can keep doing it till we get this limit n tends to infinite. So we can write this function fx as this limit n tends to infinite f 2 to the power of n into x upon 3 to the power of n. Now we need to find this limit x tends to 0 positive fx, and it'll be equal to this limit x tends to 0 positive limit n tends to infinite f 2 to the power nx upon 3 to the power n. Now range of this function is from minus 1 to 1. So this value in the numerator will lie somewhere between -1 and +1, which is a finite value, upon 3 to the power infinite, which is infinite. So value of this limit is 0. So value of this limit x tends to 0 fx is equal to 0, and that's your option D. Now question number 29 is, let psi be a continuous function such that psi y is 0 for all y which doesn't lie between 0 and 1, and this integral from 0 to 1 psi y dy is 1. We need to find this limit, which is limit n tends to infinite n into this integral from 0 to 100 fx into psi nx dx. Now what we'll do is we'll use substitution to make it some y. So we'll take let nx equals y, then dx is nothing but it is 1 upon n dy. So we can write this limit as limit n tends to infinite, and then n dx is dy. So it will be f y upon n psi y dy, and then this integral from 0, and then when x is 100 it will be simply 100n. Now we can write this as limit n tends to infinite from 0 to 1 f y by n psi y dy plus limit n tends to infinite from 1 to 100n f y by n psi y dy. Now when y doesn't lie between 0 and 1, psi y is 0. So this function is 0. So this limit will simply be 0. Now we can write this limit as from 0 to 1 limit n tends to infinite f y by n and then psi y dy. Now when n tends to infinite, 1 upon n is 0. So it will be simply from 0 to 1 f0 psi y dy. We can take this f0 out, and then what is integral of psi y dy? It is nothing but 1. So answer to this limit is f0, and that's your option number A. Now the question is, we are given this function f defined from minus pi by 2 to plus pi by 2, and f0 is 1, and this integral from 0 to pi by 3 ft dt, it is 0. Now which of the following options is or are correct? Now what we'll do is we'll assume a function gx, which is this integral from 0 to x ft dt minus sine 3t in the interval x belongs to 0 and pi by 3. Now if we find g0, it is 0 and sine 0 is also 0. So value of g0 is 0, and if we find g pi by 3, this integral from 0 to pi by 3, it is 0, and then sine pi will also be 0. So this function gx, it is continuous differentiable. g0, it is equal to g pi by 3. That means this function gx, it satisfies the condition for Rolle's theorem. Then from Rolle's theorem we can say there exists at least one c in the interval 0 to pi by 3 such that g dash c is 0. Now we differentiate this, then we can write this is fc minus 3 cos 3c equals 0. So this equation fx equals 3 cos 3x will have at least one solution in 0 to pi by 3. That means this option A, it is correct. Now for this option B, again we'll assume a function and let this function be hx, which is this integral from 0 to x ft dt plus cos 3t plus 6x upon pi in the interval 0 to pi by 3. Now this function again is continuous and differentiable. Now if we find h0, h0 will be cos 0 is 1, and h pi by 3, this integral will be 0. Now cos pi is minus 1 and this value will be 2. So value of h pi by 3 is 1. So again this function hx, it satisfies all the three conditions of Rolle's theorem. So again from Rolle's theorem we can say there exists at least one c in the interval 0 to pi by 3 such that h dash c is 0. Now if we differentiate this function, we can write fc minus 3 sine 3c plus 6 upon pi will be 0. So this equation fx minus 3 sine 3x equals minus 6 upon pi has at least one solution in 0, 3, which means this option D is also correct. Now if we look at this option C, which is this limit x tends to 0, x into this integral from 0 to x ft dt upon 1 minus e to the power x square. Now what we'll do is we'll multiply and divide it with x square. Now we can rearrange this limit as limit x tends to 0, this integral from 0 to x ft dt upon, now x and x will cancel, so it will be this x into, now this is standard limit, e to the power x minus 1 upon x, it is 1, and here it is 1 minus e to the power x square, so this value will be simply minus 1. Now this is 0 upon 0 form. If we use L'Hopital's rule, we can write limit x tends to 0 fx upon 1 and this minus, which is equal to minus f0, and the value of f0 is 1. So value of this limit is minus 1, which means this option C is also correct. Now if we look at this option D, then for this option D we can write limit x tends to 0. Now this is sin x upon x and then this integral from 0 to x ft dt upon x. Now this is tan limit 1 and this is 0 upon 0 form. So again if we use L'Hopital's rule, it will be f0 and f0 is 1. So this value is actually 1 and not minus 1. So option D is incorrect. So the correct options are A, B and C. Now here the question is, let a1 equals 1 and an equals n into an minus 1 plus 1 for n equals 2, 3, 4. Define Pn as 1 plus 1 upon a1 into 1 plus 1 upon a2 up to 1 plus 1 upon an. Then we need to find this limit n tends to infinite Pn. Now we can write this Pn as a1 plus 1 upon a1, a2 plus 1 upon a2, and in the same way it goes up to an plus 1 upon an. Now from this recurring relation we can say that an minus 1 plus 1 upon an, it is equal to 1 upon n. So we can write this as 1 upon a1 and then a1 plus 1 upon a2 into a2 plus 1 upon a3, and it goes all the way up to an minus 1 plus 1 upon an into an plus 1. Now this is 1 by 2, this is 1 by 3 and this is 1 by n. So we can write this as 1 upon factorial n an plus 1 upon a1. Now we are also given that a1 is 1. So we can write this as 1 plus an upon factorial n. Now this is 1 upon factorial n plus an upon factorial n. Now an upon n is an minus 1 plus 1. So we can write an upon n as 1 plus an minus 1. So we can also write this as 1 upon factorial n plus, and this is 1 plus an minus 1 upon factorial n minus 1, which is 1 upon factorial n plus 1 upon factorial n minus 1. Now if we continue in the same fashion, in the end we'll get 1 upon factorial n plus 1 upon factorial n minus 1 plus a2 upon factorial 2, We can also write this as 1 upon factorial n plus 1 upon factorial n minus 1, 1 upon factorial 2 plus, now a2 upon 2 is 1 plus a1 and a1 is 1. So it will be 1 plus 1 upon 1. So that's your Pn. Now we take this limit n tends to infinite Pn, it will be 1 plus 1 upon factorial 1 plus 1 upon factorial 2, and this series, it goes all the way up to infinite. It is nothing but e. So the value of this limit n tends to infinite Pn will be simply e, and that's your option B. Now question number 1 is, for any polynomial pt, the limit t tends to infinite pt upon e to the power t is independent of polynomial p. Justify the statement and find the value of this limit. So we have this limit, which is limit t tends to infinite p as a function of t upon e to the power t. Now if we put t as infinite, this numerator will be plus or minus infinite, and then e to the power infinite will be infinite. So when it is infinity upon infinity form, we can use L'Hopital's rule. And if we use L'Hopital's rule, we can write this as limit t tends to infinite p dash t upon e to the power t. Then again it will be plus minus infinity upon infinity. So we can differentiate it again. We can keep using L'Hopital's rule till we differentiate this function n times, which is degree of this polynomial. And if we differentiate this polynomial up to its degree, then it will be some constant upon infinite, and any constant upon infinite is simply 0. So this statement is true, and the value of this limit is simply 0. So that's your part A. Now part B is, show that q dash 0 exists and find its value. And why is it enough to calculate the relevant limit from only one side? Now we'll find q dash 0 positive. Now q dash 0 positive will be limit h tends to 0 q 0 plus h minus q0 upon h. Now this is limit h tends to 0. Now q h positive when x is greater than 0 is simply e to the power minus 1 by h. q0 is 0, and here it will be this h. So we can write this as limit h tends to 0 1 by h, and then e to the power 1 by h. Now what we will do is, we let 1 by h as t, then we can write this as limit t tends to infinite t upon e to the power t, which is of the form pt upon e to the power t, and we know that this limit is equal to 0. So q dash 0 positive is 0. Now we need not calculate q dash 0 negative, as this given function is an even function. So suppose we have to find the value of q minus 2 will be e to the power minus 1 by 2, and which is same as value at 2. So this given function is an even function. So we just have to calculate limit from only one side. So this q dash 0 exists and its value is simply 0. Now part C is, for any positive integer n, show that qn0 exists and find its value. Here qx is the function in part B, and qn0 denote the nth derivative at x equals 0. Now what we'll do is, for this part C, we have to find nth derivative of this function at 0. Now we know that qx, it is an even function. Now if qx is even, q when x is odd, q2x is even, and continues. So we can say this q and x will be even when n is even, and will be an odd function when n is an odd function. So we can simply write qn minus x will be minus 1 to the power n q nx. Now, if we look at this function, which is qx, when x is greater than 0, it is e to the power minus 1 by x. Now, q1x will be e to the power minus 1 by x into 1 upon x square. Now, if we find q2x will be e to the power minus 1 by x minus 2 upon x cube plus 1 upon x square e to the power minus 1 by x, and then 1 by x square, which is e to the power minus 1 by x minus 2 upon x cube plus 1 upon x to the power 4. Now we keep differentiating it. We can write qnx will be of the form e to the power minus 1 by x and then some polynomial expression of 1 by x. Now if we have to find qn0 positive, it will be this limit h tends to 0 e to the power minus 1 by h p 1 by h. If we let 1 upon h as t, we can write this as limit t tends to infinite pt upon e to the power t, and this we have already established in part A that this is equal to 0. So from here we can say this qn0 positive will be equal to qn0 negative and will be equal to 0. That is, this qn0 will exist and it is equal to 0. Now question number 24 is, let f from R to R be a continuous function such that limit n tends to infinite fnx exists for every x belongs to R, where fnx is composition of f n times for any n greater than or equal to 2. We have defined two sets, set S as limit n tends to infinite fnx for x belongs to R, and then the set T, which is fx equals x for x belongs to R. Now we'll start with this limit. Limit n tends to infinite fnx and let it be some function, say hx. Now since f is continuous, we can write this hx as f and then limit n tends to infinite f n minus 1x. This limit n tends to infinite f n minus 1x will again be hx. So from here we can write hx is equal to f of hx, which again is of the form x equals fx when x lies in range of fx. So our set S is x equals fx for any x which lies in the range of fx. Now the set T, it is given as x belongs to R and fx equals x. Now both these sets, they look equal, but then here the crucial information is this S is when x lies in the range of fx. So essentially this S, it has to be subset of T. So answer to this question should have been S is a subset of T. ISI has given the answer as C, which is S equals T, considering x equals fx as same for both the functions. But then it is entirely up to the interpretation. Now question number 18, it says let Pn be number of digits when 8 to the power n is written in base 6, and let Qn be number of digits when 6 to the power n is written in base 4. We need to find this limit, which is limit n tends to infinite Pn Qn upon n square. Now there is a direct formula for that. So if we write 8 to the power n to the base of 6, then number of digits Pn, it is given by greatest integer function of log 8 to the power n to the base 6 and then plus 1. So this is the formula to find out number of digits in other base. So in the same way, we can find number of digits Qn when the base is 4. So Qn will be log base is 4 and number here is 6 to the power n plus 1. So basically Pn is n log 8 base 6 plus 1 and Qn is greatest integer n log 6 base 4 plus 1. Now we need to find this limit, which is limit n tends to infinite Pn into Qn upon n square. Now in greatest integer function, we know this property that greatest integer function of x is always less than or equal to x and it is greater than x minus 1. So I can write Pn is less than or equal to n log 8 base 6 plus 1 and it is greater than n log 8 base 6. In the same way, we can write Qn. So Qn will be less than n log 6 base 4 plus 1 and here will be n log 6 base 4. Now if we multiply them, then we can write it as n square log 8 base 6 into log 6 base 4 is less than Pn into Qn and it is less than n log 8 base 6 plus 1 into n log 6 base 4 plus 1. So now I'll need to find this limit. So I'll need to divide it with n square. So I'll also divide it with n square. So if I'll divide it with n square and I'll take this limit also. I'll take this limit n tends to infinite. Now since it is an infinite limit, so highest power of n in the numerator and denominator is 2. So answer to this left hand limit will be simply log 8 into log 6 and here it is limit n tends to infinite Pn Qn by n square, and here also the highest power is n square. So here also this limit will be log 8 base 6 into log 6 base 4. Now Sandwich theorem says if fx lies between gx and hx and if limiting value of gx is L and limiting value of hx is L, then the limiting value of this limit is also L. So which simply means the value of this limit is equal to log 8 base 6 into log 6 base 4. So I can write it as log 2 base 8 upon log 6 base 2 and here will be log 6 base 2 upon log 4 base 2. So it will cancel. So 8 is 2 cube and 4 is 2 square. So the value of this limit is simply 3 by 2 and that's your option number C. Now question number 8b is we are given a sequence in which a0 is 1 and a1 is 1 and for n from 1, 2, 3, 4 it defines an plus 1 as 1 plus an minus 1 square by 4. Now the question is, does the sequence an converge to a finite limit as n tends to infinite? And if it does, we need to find this limit. In the first part, we'll prove that this an plus 1, it is bounded. So we'll show that an plus 1 will lie between 0 and 1 and we'll prove this by induction. So our statement is for any n greater than or equal to 1, an plus 1, it is greater than 0 but less than 1. Now we'll put P1. Now P1 is actually A2. Now what's A2? A2 is 1 plus A1. A1 is 1. A0 square. A0 is also 1. So divide by 4. So it is 3 by 4. So value of A2 lies between 0 and 1. Now we'll assume that it'll be true for any value of k starting from 1 to n. So we can write ak minus 1 will lie between 0 and 1 and ak will also lie between 0 and 1. Now we'll need to prove that this statement is true for k plus 1. So for k plus 1 we can write ak plus 1 as 1 plus ak minus 1 square upon 4. Now we know that ak lies between 0 and 1. ak minus 1 also lies between 0 and 1. Now we'll square it. We'll write 0 and then ak minus square will also lie between 0 and 1. So we'll add them. We can write 0 and ak plus ak minus 1 square will lie between 0 and 2. Now we'll add 1. So we'll add 1. We can write 1 is less than 1 plus ak minus 1 square, and it is less than 3. Now we'll divide it with 4. This is nothing but ak plus 1. So from here we can say this ak plus 1 will be greater than 0 but less than 1. So from induction we have proved that any term for the sequence will always lie between 0 and 1. Now we need to find the limiting value of the sequence. So what we'll do is here we'll take limit n tends to infinite. So it'll be limit n tends to infinite, and it'll be equal to this limit n tends to infinite 1 plus an minus 1 square upon 4. Now suppose this limit exists and it is equal to L. So this is L and here it will be 1 plus. Now again when n tends to infinite, this is limiting value of the sequence. So it will be again L and here will be L square by 4. So from here we'll get this condition, which is L square minus 3L plus 1 equals 0. Now it is a quadratic equation in L. So we'll solve this equation. We'll get L as 3 plus minus under root of 9 minus 4 by 2. So limiting value of the sequence will be 3 plus minus under root 5 by 2. Now in the first part we have already proved that this ak plus 1 should be less than 1. So the only value possible in this case is 3 minus root 5 by 2. So the sequence, it converges to a finite limit, and that finite limit is 3 minus under root 5 by 2, and that is the answer to this question. Now let us take one question in limits, and this problem was asked by one of my students. It says let fx equals 8x cubed plus 3x and f inverse be the inverse of fx. Then we have to find this limit x tends to infinite x to the power 1 by 3 upon f inverse 8x minus f inverse of x. Now what we are given is, we are given fx is 8x cubed plus 3x. Now we find f dash x will be 24x square plus 3, and it is always greater than 0. So that means this function fx, it is strictly increasing. And if we find f double dash x, it will be simply 48x. That means its point of inflection is at x equals 0. So this function, it will be strictly increasing function which will intersect the axis only at x equals 0. Now we have to solve this limit, which is limit x tends to infinite x to the power 1 by 3 upon f inverse of 8x minus f inverse of x. Now what we'll do is, we'll say let f inverse of 8x is z and let f inverse of x be some y. We'll write let f inverse of 8x equals z and f inverse of x as y. Now we can write f inverse of 8x equals z as 8x equals fz. Now what's fz? Fz will be 8z cube plus 3z. So we can write this as 8x equals 8z cube plus 3z. Now what we'll do is we'll take 8z cube common. So we'll write 8x equals 8z cube 1 plus 3 by 8 z square. Now we'll cancel this 8 with 8 and we'll take cube root both sides. We can write x to the power 1 by 3 equals z 1 plus 3 upon 8 z square to the power 1 by 3, or we can express z as x to the power 1 by 3 upon 1 plus 3 by 8 z square to the power 1 by 3. Now in the same way, we can solve this other condition, which is fx equals y. We can write x equals fy. Now fy is 8y cube plus 3y. Again we'll take 8y cube common. We'll write 1 plus 3 by 8 y square. And if we take cube root again, we'll get x to the power 1 by 3 and it'll be equal to 2y 1 plus 3 by 8 y square to the power 1 by 3, or we can write y as x to the power 1 by 3 upon 2 1 plus 3 by 8 y square to the power 1 by 3. Now what we'll do is we'll put the value of z and y in this limit. Now we can write this limit as limit x tends to infinite x to the power 1 by 3 upon z minus y. Now z in this case is x to the power 1 by 3 upon 1 plus 3 by 8z square to the power 1 by 3 minus x to the power 1 by 3 upon 2 1 plus 3 by 8y square to the power 1 by 3. Now we can cancel this x to the power 1 by 3 from the numerator and from the denominator. Now we have to find the value of this limit z and y when x tends to infinite. Now z is f inverse of 8x and y is f inverse of x. Now this function fx, it is an increasing function. So as x tends to infinite, fx tends to infinite. And if we talk about inverse function, its inverse function is nothing but it is reflection of fx about y equals x line. Now for inverse function also, when x approaches infinite, f inverse will also approach infinite. So it simply means that when x tends to infinite, z tends to infinite and y tends to infinite. And if z and y, they both approach infinity, then in that case 3 by 8z square will be 0 and 3 by 8y square will also be 0. So value of this limit in this case will be 1 upon 1 by 1 minus 1 by 2, which is nothing but 2. So answer to this limit is 2. And that's your option C. Now the question is, let A is nth power of this matrix 2, 1, 1, 0. And we need to find this limit n tends to infinite A1, 2 upon A2, 2. Now let this matrix be B, and which is 2, 1, 1, 0. And we'll write this as this 1, 0, 0, 1 plus 1, 1, 1 minus 1. So this is I and this is suppose C. So we can write this B as I plus C. So now we have this matrix C, which is 1, 1, 1 minus 1. Now we find C square will be 1, 1, 1 minus 1 and then 1, 1, 1 minus 1. Now we multiply. We'll get this as 2. Now this is 0. This is 0 and then it'll be 2. So C square is basically 2i. So once we have this expression, then we know that C square will be equal to 2i, and if we multiply it with C, we'll get C cube as 2c. And we multiply it again with C, we'll get C to the power 4 as 2c square, and 2c square is 2i. So there'll be 4i. C to the power 5, there'll be again 4c, and this sequence will continue like that. Now we have assumed this B is I plus C. Now we take nth power of B, then it will be I plus C to the power n. Now we can write this as B to the power n equals nc0 into I plus nc1 into c nc2 into c square nc3 into c cube, and this series will continue up to ncn into c to the power n. Now for even powers of c, it will be simply 2i, nc4 will be nc4 into 4i. So we can write this as nc0 plus 2 into nc2 plus 4 into nc4 into I, and then plus, now this is c, now c cube is 2c, c to the power 5 is 4c, so we can write this as nc1 plus 2 into nc3 plus 4 into nc5, and it will be multiplied with c. Now we need to find sum of these two series. So this is our first series and this is our second series. Now say this is P and this is Q. Now we consider the expansion of 1 plus root 2 to the power n, it will be nc0 plus nc1 into root 2 nc2 into root 2 square nc3 into 2 root 2. Now if we consider these terms, this is nothing but p, so it will be this p, and then if we take root 2 common, then it will be q. So we can write this as p plus root 2q. So value of p plus root 2q will be simply 1 plus root 2 to the power n. And if we take 1 minus root 2, it will be alternate plus minus, then we'll get p minus root 2q, and there will be 1 minus root 2 to the power n. Now if we add them, we'll get the value of p. So we'll get this p as 1 by 2 into 1 plus root 2 to the power n plus 1 minus root 2 to the power n, and if we subtract them, we'll get this q as 1 upon 2 root 2, and then it'll be 1 plus root 2 to the power n minus 1 minus root 2 to the power n. So now we have worked out values of p and q. So basically we can write a, which is b to the power n, and there will be pi plus qc. So this a will be this pi, so it will be p 0, 0 and p plus q into c. Now c was 1, 1, 1 minus 1, so there will be q, q, qn minus q. So this a will be p plus q, and this is q, this is q, and this is p minus q. Now it says we need to find this limit n tends to infinite a12. Now a12 is first row second column, which is this q, upon a22, and a22 is p minus q, and it's given that this is equal to L. Now this is limit n tends to infinite. Now q is 1 upon 2 root 2, and this is 1 plus root 2 to the power n minus 1 minus root 2 to the power n whole divided by, now p minus q, and p minus q will be 1 by 2, 1 plus root 2 to the power n plus 1 minus root 2 to the power n, and minus 1 upon 2 root 2, 1 plus root 2 to the power n minus 1 minus root 2 to the power n. Now we'll divide everything with 1 plus root 2 to the power n, and then we'll write 1 minus root 2 upon 1 plus root 2 as some lambda. So we can write this as this L will be equal to this limit n tends to infinite. This is 1 upon 2 root 2, 1 minus lambda to the power n upon 1 by 2, 1 plus lambda to the power n minus 1 upon 2 root 2, 1 minus lambda to the power n. Now this lambda, it lies between 0 and 1. So lambda to the power n as n tends to infinite will be simply 0. So value of this limit will be 1 upon 2 root 2 upon 1 by 2 minus 1 upon 2 root 2, which is 1 upon root 2 minus 1. And if we rationalize, we can write this as root 2 plus 1. So value of L is root 2 plus 1. So value of L is root 2 plus 1. Now L square will be 2 plus 1 plus 2 root 2, which is 3 plus 2 root 2. Now we can write this 3 as under root 9 and we can write 2 root 2 as under root a. So value of a and b, they can be 8 or 9 or 9 or 8. Then the value of a plus b will be 9 plus 8 and which is 17. So answer to this question is 17.
Hello and welcome to the world of mathematics. I present my website www.mathsmarazing.com and my YouTube channel Mathsmarazing for your kind perusal. If you like them and are inspired by the possibilities, then consider subscribing and sharing it with someone you know who might benefit from it. Thank you.